right? So even now, even if you don't care about building a quantum computer, I would make the point that unless you abdicate your capacity to really be, involved in the cutting edge of technology, you need to have some understanding of how the quantum world works, right? The transistor you have in your pocket is, on the tens of nanometer scale. You have no chance of understanding what's going on in there unless you understand some quantum mechanics. And, some people and some places may have a bit of a black boxing attitude. It's like, there's someone out there in Silicon Valley understands that stuff. I just want to make an app to deliver pizzas, And that's okay, but I think it's a bit unambitious,
Got it.
We can do better than that. And Australia has a strong presence and a strong background in the quantum technologies, and I think we have a real opportunity to be a hub for quantum engineering.
Fantastic.
Which doesn't mean forgetting all we know about the classical electronics engineering. It just means blending it and upgrading it to what are the nanoelectronics, microwave engineering technologies that are coming up.
Do you ever see a point where people will be doing quantum computing, a straight quantum computing degree at university instead of classical? Will there be that much demand that, there'll be whole courses devoted just to quantum computing, learning quantum computing?
Yes, I would call it quantum engineering.
Quantum engineering, okay.
So there might be...
when does it stop being engineering and becomes just general computing?
Well, I'm speaking maybe from my, background of electronics engineering. I see mostly the hardware part of things, and then we also teach, of course, a bit of software and some of the communication protocols. In the computer science department, they might think, wow, one day we will have a whole school of quantum software. And in fact, some places like UTS here in Sydney, they have masters in
really?
that already.
Interesting.
Yeah, so we are working more at the undergraduate level. So at UNSW, we are developing essentially a quantum engineering offering that is at the undergraduate level.
Okay, so
which is really quite unique.
Elective course that they can take as part of their normal degree.
Yeah.
Okay.
That's already there now.
Right.
And then we are looking at, in the near future, really making it an actual stream, an actual degree that you can...
Right. Because a lot of engineers will, regular practical electronics design engineers won't believe it until they can buy the chip on DigiKey or somewhere. They just won't believe it until they can physically...
That TV is called a quantum.tv for a reason, right?
Oh, true.
I just bought this TV 2 months ago. It's a QLED. That Q stands for quantum dots.
Quantum
I mean,
dots.
it's not.
Okay.
It's not science fiction. It's on the wall.
It's science fiction. Okay. Right? Yep. But as we talked about before, at the moment, you can't really see a practical way of doing it without going to the super low temperatures.
That's perfectly fine. There's no issue with that. Right. On the topic, before I forget, there's a very important document that was launched by CSIRO just maybe 3 weeks ago. Is the Quantum Technologies Roadmap for Australia. Ooh. They spent a significant amount of time and effort really mapping out what is the prospect for quantum technologies industry in Australia. And they estimated 4 billion revenues and 16,000 jobs by 2040.
By next 20 years?
2040,
okay.
Yeah.
Wow.
And if you speak to they had a webinar sort of launch of this Quantum Technologies Roadmap. And there were a number of people participating there, including a venture capitalist. And he, as an investor, he thought that those numbers were really, really underestimated.
Oh, okay.
Yeah.
Right. Somebody wanted to know, is there any way that, people interested in this sort of stuff can experiment in their own labs? Is there any, or do you really need the liquid helium? And do you need the 40 gig transmitters and the...
Okay, so in the context of these quantum engineering courses that we teach at UNSW, we've actually developed labs for students.
Okay,
yeah.
Right.
So some colleagues of mine have in fact built up this little lab that the students do where you can control and measure a single spin
That's all I'm talking about. Just you know, not doing
at room
anything serious.
temperature.
Yeah. Oh, okay.
There is a particular system, it's called the nitrogen vacancy center in diamond.
Ooh.
It's a color center in diamond. It's one of those defects in the diamond crystal that give it a bit of a color.
Yes.
And it turns out this defect has a spin. And this spin has an energy splitting that's created by the crystal field. So you don't even need a magnetic field for it. If you apply a magnetic field, you can shift it a bit. But it has an intrinsic splitting of 2.7 gigahertz, which is a nice number.
Which is doable.
It's doable. And then you say, okay, but at room temperature, 2.7 gigahertz is much less than the thermal energy.
Yes.
In fact, it works nonetheless because diamond is a very stiff crystal, which means that the frequency of the thermal vibrations of the diamond crystal is extremely high. It's like, imagine a massless spring model. It's like having very light masses, because carbon is a light atom, and very stiff springs.
Right.
Whereas this spin has barely any interaction with that crystal lattice. So the spin essentially doesn't know what the temperature is.
Oh, interesting.
Right? The spin, I mean, it will eventually, after a couple of milliseconds, it will find out what the temperature is. But you have a window of time where you can thermally insulate it and you can play with it.
Interesting.
And so, in fact, my colleagues have published the paper where they describe how this little student's lab is built, and you know, it's actually on the public archive. So if someone wanted to,
somebody wants to have a play with
have
that,
a play, you know, there's, I don't know how much you would call. There's probably a few $1,000s of, you know, like you need some radio frequency sources, you need some digitizers. There's a few $1,000s worth of stuff, but it's not. You don't need a refrigerator in your room, you know.
Exactly.
And especially if you are an electronics engineer, you may have some of the instruments already in your lab, you know,
exactly.
So.
Okay.
Yeah. So it's not out of this world.
Okay.
It's not out of this world.
So people can have a little.
People can have a little play
if they want.
Yeah.
Interesting.
The other thing people can do is to log on to the existing and openly accessible quantum computers that companies like IBM make available.
Oh, they do.
They do. So there's something called the IBM Quantum Experience, which is a 5-qubit superconducting processor that's in the cloud.
Oh.
So you can go on that website, make yourself an account. And you can program that quantum computer. Will give you back the results. There's lots of people who use it for teaching, for example. You know, like you can get your students to log on to that. You give them an assignment, and they use that IBM Quantum Experience for doing these things. Of course, there you don't, you know, you interface with your terminal. It's not the same as making your own thing, but it is a legitimate 5-qubit quantum computer that you can access remotely.
Fantastic. I've heard that there's, what languages are there? I've heard about Q-hash.
And then there's Qiskit. There's a couple of languages out there. Okay. There's Liquid. There's the one for simulations from Microsoft. There's a couple of ones.
And how do they differ from regular procedural or object-oriented
They look
languages?
a lot like assembler. They're really low level.
Right.
They're reasonably low level languages.
Right.
Yeah.
So you can just, you know, flip this quantum bit, read this one, that kind of stuff.
Yeah.
Right.
There's even people, there's colleagues of mine who, I don't know what stage it's at, but some time ago they were telling me about, they were developing some quantum games. It's basically video games where the rules of the game are the quantum rules. Yeah.
Oh, interesting. Okay, at an abstract level, I'm guessing, kind of.
No, they're real rules. Okay. I never had enough time to actually play with them. You know, I wish I could. You know, I wish I was a teenager and had time to play with this.
Exactly. You don't have responsibilities. You know, join the club.
All the things I would do if I had the time.
Yes.
You know?
Oh, tell me about it. Give us your best and worst case predictions for, say, the next 20 years. Like worst case is in, oh no, it all just peters out. No, there's nothing really practical. It doesn't work. And what's the,
Look,
I know you said you don't like giving.
No, I'm going to be really cheeky here.
Please do.
You see, I'm a legitimate electrical engineer. I've got a degree in electronics engineering, and I teach, electromagnetism in third year. So I'm one of you, okay?
Okay.
But I'm also someone who has a genuine passion for the fundamental questions in science.
Yep.
So for me, you see, quantum computing is a win-win bet. I see two scenarios. Either it works, like it actually works.
Are you talking practically
For
works?
practical things.
For
So
practical
you
things.
can act.
It works now.
Yeah.
But
So either you can actually build a scalable quantum computer, meaning you have figured out the fundamental logic gates, you have an error budget that is under control, you have protocols to detect and correct the errors that keep you below a correction threshold, that the thing actually scales up.
Right.
And you can manufacture it, and your manufacturing tolerances are compatible with the errors that you're able to tolerate for your quantum computer, and you just make the thing, and the thing works. And you can run algorithms on it that give you interesting and useful and beneficial results.
Right.
That's scenario one. Great, right?
Yeah, fantastic. Holy
Scenario
grail.
two, it doesn't.
It doesn't. You can't
And
do
it
that.
doesn't
All right.
because of some fundamental law of physics we haven't discovered yet.
Got it. So something you can't foresee it at the moment.
You can't
but
foresee at the
But
moment.
you can't rule it out that it may not be possible.
Maybe there is some fundamental constant that limits
The
the
practicality.
quantum information you can
Right.
encode. There have been some, people have been wondering in the sort of fundamental quantum science community, the problem of how does the microscopic quantum world morph into the classical world we experience at the large scale,
Yes.
right? And some people think it's a non-question, it's just a kind of stupid thing to even ask. Some people come up with various theories for what it could be, and some people have even imagined that there might be some scale, which could be a size scale, it could be a mass scale, or it could be an information density scale, at which for example, the Schrödinger equation as we know it, which is a linear differential equation, is no longer exact. It gets some correction terms.
Okay.
And those correction terms have a prefactor, have a constant in front of it, that if you're making, a 10 qubit quantum computer is irrelevant if you're making a 10,000 qubit quantum computer starts to affect things.
Ah, interesting.
Right? I'm not saying that this is what's going to
No,
happen,
but
right?
it could, in theory.
But I see two scenarios. Either we're done with physics. I mean,
Come on,
sorry.
that's going to come back to haunt you, that one.
Yeah. Either, the physics we know is correct enough that we can
Correct.
use it to manufacture a quantum computer that works, or it's not.
Or it's not.
Or it's not. So for me, both scenarios
Scenarios.
are fantastic. I will take both. I will take both.
Is that Andrea's cat? Is that like a Schrodinger's
Andrea's
cat?
cat.
That could
It's
be
not just me, but,
Andrea's cat. Okay.
Yeah.
Both
That-
scenarios are alive and dead at the same time.
Yeah.
Yeah. Okay.
We'll find
All
out.
right.
You see, my wild dream is to, have developed the technology to make, quantum bits in silicon, have it all under control, have it, have some deal with some foundry, and we get it all manufactured with the latest equipment, the fanciest technology. And we make a 100 qubit circuit, and you run it, and it works. You make a 1,000 qubit circuit, and you run it, and it works. You make a 10,000 qubit circuit. Scales. And then eventually it just stops.
Yeah, that'd be disappointing, wouldn't
That would be amazing. That would be amazing. That would be like to actually watch in an engineered electronic device a new law of physics.
it could pop out. A new law of physics could
Electronics
pop out.
engineering, listen to this, my friends. Electronics engineering enabling the discovery of a new law of physics.
Wow,
That's
that
what
would
I
be
work
something.
for. That's what I work for.
Wow.